Hello everyone, we are near the end of chapter 6 and I wanted to cover surface level winds and the fact that they cross isobars at more or less right angles, give or take the Coriolis and give or take the centrifugal and or centripetal force that gives it a curve in or a curve out. But basically, these cross isobars at the surface winds and on the surface map, but the upper level winds blow parallel to the contour lines. They're not crossing the contour lines. So why the big change? And actually, it's not a big change at all in the physics. It's just a big change in the way the data is analyzed. So let's look over that. Here's a complicated slide, but I'm going to walk you through it. I would normally put this up on a board, and draw it all out, but I can act it out for you here. So on the upper level maps, the difference is that the map is all one pressure. And in fact, we're looking at altitudes for that one pressure along like a surface of one pressure. At the same time, the atmosphere in the upper levels still has horizontal pressure gradients, because this can be my 500 millibar surface, and this can be my higher 300 millibar surface. And if I took the horizontal movement in this atmosphere, I would go from 500 millibars to 300 millibars. I would go from high pressure to low pressure. And so that's what I'm trying to show you here. Here is a 500 millibar surface, and above it is a 300 millibar surface. Now, when you're thinking about the atmosphere, you're going to go from high pressure to low pressure on a horizontal wind. So you're going to go from the 500 millibar surface straight to the 300 millibar surface. You're still doing that. It's just that this map doesn't represent that well. And when you go from 500 to 300 millibars, especially at the upper levels where there is no friction, then the Coriolis effect is going to be in full force, for lack of a better word. And it's going to be pulling dramatically to the right in the northern hemisphere. As a result, in the upper levels, you're going to wind up with a western wind that balances the pressure gradient force, which still exists in the upper levels, and the Coriolis force, which is, well, the Coriolis effect, which is at its maximum in the upper levels because there's no friction. That westerly wind, now I realize I'm trying to work the angles here, that westerly wind is going to go with the contour lines. The contour lines on the upper level map are the lines for 5,580 meters and 5,640 meters. So in other words, this is dropping in altitude for the 500 millibar map, and you are looking at the contour lines in gray. And this wind is parallel to those contour lines because this wind has been moved in a more or less westerly direction. Another way to look at this, and this is in your book, this is all covered between pages 155 and 159 in your book. But in looking at this, what I want you to know is that this prevailing westerly wind is not only in the northern hemisphere, it's also in the southern hemisphere. It's not a big point, and we can explain it further, but if you want to look into that further, it's on page 164 of your text. The point being that you've been hearing about the Coriolis effect having the opposite force on the northern hemisphere and on the southern hemisphere. The Coriolis effect is one part of wind, and remember the pressure gradient force is the primary driver of the wind. And so in looking at that, you are really looking at the horizontal movement from high pressure to low pressure. That is the same from the southern hemisphere and from the northern hemisphere. The high pressure in the upper levels is from the equator, moving toward the low pressure at the poles. Same thing at the southern hemisphere. The high pressure is at the equator, moving toward the poles in the southern hemisphere. Now think about it. In the southern hemisphere, it moves toward the poles and it takes a left. And guess what? As it goes up from the equator and goes toward the poles and takes a left, guess what? You have a westerly wind. So very interesting. If you want to explore it more, you could look into page 164. To the next one. What I want to point out to you here is that these 500 millibar maps actually double the surface wind speed, roughly. And so you can take an observation of the surface wind speed, double it, and see what it is at the tracking level of 500 millibars. Really important map for us. Let's include a little bit more information about why that happens. If we look at the upper levels at these higher speeds, and then we come down closer to the surface, near where skyscrapers might be in New York, you'll notice that it's roughly half the wind speed down there. And it's easy to understand why when you look at the pressures, because remember, the pressures drive the pressure gradient force. So at the 500 millibar level in the upper levels, you've got maybe a 4 millibar interval that is driving the pressure gradient force, much like the 4 millibar interval that you know about from surface maps. But if you think about it, 4 millibars out of 500 millibars is about less than 1%. But 4 millibars out of something much closer to the surface, much closer to the 1,000 millibar level of the surface, skyscrapers that are about 900 millibars, that is much less difference. It's even less than 0.5%. So about half the difference. That's why you have about double the wind speeds aloft at the upper levels. And I want you to know that because the pressure gradient force of those pressure gradients really drives everything else for wind speed. If the pressure gradient force is lower, then the Coriolis effect doesn't have as much impact because the wind speeds are lower. If the Coriolis effect doesn't have as much impact, it doesn't pull to the right as much. If it doesn't pull to the right as much, you get a bit off the westerly wind. You don't get the pure westerly wind that you get in the upper levels. Like I mentioned here, there's another part of that. The wind slows down even a little bit more at the skyscraper level because now friction comes into play. You've got a building out in the middle of you, and the wind needs to change direction to go in the path of least resistance. So now you've got lower pressure gradient force that is lowering the wind speed, and you've got friction because you have things in the way that is lowering the wind speed as well at the skyscraper level. If we go down to the surface level, where you've got grass and fields and so forth, you've got even lower pressure gradient force, and you've got more things in the way. You've got trees in the way rather than skyscrapers. So what you see here is that the net force turns out to be the purple force here of a southwesterly wind. So this is deflected about 60 degrees from the right of the pressure gradient force, whereas in the upper levels, you had 90 degrees from the right of the pressure gradient force and you had a westerly wind. Here you've got about 60 degrees off the pressure gradient force for a southwesterly wind. You might hear it discussed as about 30 degrees off of the parallel to the isobars. So here's the isobar, and here's another isobar. And if you were looking at an isobar in the middle, you would be about a 30-degree angle off the isobars here when you are at the surface. Again, friction is going to become even more important and slow the wind down even more. And the friction adds a force that is opposite and proportional to the net force, which is the surface wind. So the friction acts in the other way, proportionally and opposite to the net force on the surface wind. Quick review. These surface winds are going to show less pressure gradient force and consequently less wind speed and consequently less Coriolis effect. And the winds at the surface are going to cross isobars at about 30 degrees off the parallel to the isobar. So about there. Friction reduces that wind speed even more. And in the upper level charts, you're going to notice more pressure gradient force and faster winds and more Coriolis effect. And that is going to tilt the wind over to the right, deflect it over to the right, so it's parallel with the contour lines. And you're not going to have friction at the upper levels. No trees, no buildings. Go on to one last thing. A couple details. In regard to the upper levels, they have a special name. They're called geostrophic winds. And geostrophic is a combination of two words. Geo meaning earth in Greek. Strophic meaning turn or bend in Greek. The Coriolis effect bends and deflects the wind to the right. So upper level winds are known as geostrophic winds. And conversely, I want to go over the fact that geostrophic winds have a net force of 0. Now you may say, these are very, very strong winds, and they are. They can go up to 250 miles an hour. And how can they have a net force of 0? Well, it depends on how you identify and define force. We define force in physics as F equals ma. Force equals mass times acceleration. The mass is the mass of all air molecules that are moving. The acceleration is all the acceleration of the air molecules. But how do you define acceleration? You define acceleration as speed and direction of the air molecules. Well, in this case, when we get to geostrophic net force and we get to a geostrophic wind, that's going to have a constant wind speed. It gets up to 250 miles an hour and stays 250 miles an hour. That's a constant wind speed. That means that the change in speed is 0 because it's constant. Okay? Now we talk about direction, and when we produce a geostrophic wind that is parallel to the contour lines, then its direction is not changing until the contour lines change. When you are in that situation where there is no change in direction, that change in direction is equal to 0, and no change in speed, that is equal to 0, then the acceleration is equal to 0, and F equals ma becomes force equals mass times 0. Well, anything multiplied by 0 is 0, so that means the net force is 0. So I want you to know that geostrophic net force of winds is 0 joules, right? Actually, I take that back. 0 newtons. Thank you. That's the unit we use for force. See you on the other side.